Okay, in this video I'm going to walk you through a study guide we used just to go through some problems, and this is for universal gravitation and circular motion. First thing you should do is find your equation sheet and make sure you know where all these equations are. Find the circular motion section, and also don't forget, this is something where if you're looking on the front of the equation sheet you're not going to see it, but the sound and waves, you'll see two formulas. Let's just go through the different variables. FC stands for centripetal force, and the unit is newtons. Mass is going to be kilograms. So let me go ahead and, so this is going to be centripetal force newtons. This is going to be the centripetal acceleration, and that's going to be meters per second squared. Don't know what's going on with my pen. Meters per second squared, just like any acceleration, but this is going to be an acceleration that happens because of a turning, not actually because of a changing speed. And so we have that. Here we have the velocity, and so that's going to be tangential velocity because it is going to deal with circular motion. And in order to have, for circular motion, you're going to need that centripetal force. It's always going to be directed in, so be aware of that. And therefore, centripetal acceleration is going to be directed in because force causes acceleration in the same direction. And once again, this is a turning acceleration. It's a changing direction, not actually the velocity. The tangential velocity will stay the same the whole time. And if you released a ball or something from its path, it would go directly ahead, straight ahead, tangent to the circle. So if it was released, if it was going around and around and around and around, and it was released right here, it would go straight ahead from that point. Okay, the next thing, so that's meters per second. Next thing you should watch out for is radius. One thing to note that the radius, depending on how they word the problem, it could be the distance between planets that are rotating around each other. So it could be distance, or it could be stated as the radius of the circle or the distance between the planets. So just watch out for any radius or distance in the case of the force of gravity equation below. They might use the term distance or radius. If you were using this equation down here, the force of gravity equation, well, if you're standing on the Earth, you're practically nothing versus the center of the Earth. So they might say radius of the Earth, and that might be the distance you use. So just watch out, and therefore distance and radius could, depending on how it's worded, be the same thing. Okay, so that's meters, and then now back to the centripetal acceleration, velocity. We dealt with all these variables. You see them all up here. Tangential velocity, this is nothing more than distance, but the distance of us to get around a circle. So 2 pi r is actually the circumference, so that's 2 pi r. And then period is actually a special time. It's a time it takes to go around the circle. So even though it is in seconds, it is the time it takes to go around one time. So just a single rotation around here. So it's special. It's not just time, because it might say the question might say that the time it did 50 rotations in 60 seconds. That 60 seconds is not period. But if they say one rotation in whatever 5 seconds, well, that now is period because of one rotation. Then we get to this equation. Once again, force of gravity. This could be, in some problems, weight can be calculated two ways. In the previous unit, we said Fw equals mg. This was acceleration due to gravity, and we use this as a simple way to calculate a rate. But really, this comes from this equation right here. The force of gravity is the g, and this is capital G. This is not little g. This is not 10 meters per second squared. This is that g right there. 6.67 times 10 to the negative 11th. Just ignore this unit. It's there just so that all these things, when they're all said and done, they're going to cancel out and you're going to be left with a Newton. So don't worry about this. This is not mathematical. G is 6.67 times 10 to the negative 11th, and then it has this Newton, but it's not something you're going to add into an equation. We have mass 1, mass 2. It doesn't matter what you call mass 1 and what you call mass 2. So if you're reading about you and the Earth, well, whichever one you see first, I can't write for some reason, whichever one you see first is going to be your mass 1, and whichever one you see second is your mass 2, and if you change it, it doesn't really matter. As long as you stay consistent, once you pick which one was mass 1 and was mass 2, then you're going to stick to that. Here you have distance, and once again, like I said before, it's probably going to be stated as a distance between two objects, but if there's circular motion going on, or not, in this case, if there's circular motion going on, you're not really going to use this equation. You're going to be using that equation up here, the FC equation. But if there's just the force of gravity between two objects, you're going to be going to this equation. So watch out. If you see two masses, good chance you're going to be using the force of gravity equation. And then lastly, F is frequency. So we haven't seen this much. And the unit for frequency is hertz. So watch out for that, something that we're going to work a lot more with next year when we get to sound and waves. And then period is going to be, once again, seconds, but not just seconds, seconds to go around one rotation. And then this is just, these are inverse of each other. You'll get to it later on, but period is the number, is the time per cycle, and frequency is cycles per time. And so they're just inverse of each other. You just take one, flip it over. Just find it. It's on, if you go to our school, you're going to find it in the sound and waves equation section of the equation sheet. Okay, so let's just review some basic things that we've covered. The force of the law of universal gravity deals with the force of gravity being created by this universal gravitation constant. It's a very, very, very small number. This is 0.00000000001, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry, I'm running out of space. This should actually be 10 zeros, and then at that point in time, well, you get my point. At that point, it's a really, really small number. At that point in time, you get the 6.67. So this means that you need really large masses. These masses have to be big, or at least one has to be really big, like Earth. If you're standing on Earth, you need the Earth's mass being so massive. One's going to, if I drew you to scale, it will be smaller than that dot. That is you're the mass 1 and the Earth is the mass 2, because the Earth is mass 2 and so massive that there is actually a force of gravity that you can feel. That's going to be your weight. And then don't forget, if this is not a law of ones problem, you're going to use 6.67 times 10, and that should be to the power of -11. If you know how to use your calculator, when you do the scientific notation, there's usually an exponent button. And when you type it into a calculator, it usually looks like it, once again, depends on your calculator. If I typed into that calculator, in my calculator, it would said 6.67 E and just -11 right next to it. It would look just like that when you typed it in using that. But do if you're getting the questions right all the time, keep on doing what you're doing before. We have two masses and we have the distance between them. G never changes, so that's why in the law of ones it would be a 1, but in any other question where you're actually using something kilograms and something meters, then G is going to be 6.67 times 10 to the power of, once again, to the power of -11. The formatting on this is just kind of weird. Okay, so there's this one just going at it. If this equation was used for the moon and the Earth, whichever one you want to pick, I picked M1 being the moon, M2 being the Earth, distance being that distance right here from the center to the center. And another thing to note is the force of gravity is inversely related. When I say inversely, but inverse square, watch out. It has a really big effect. If you were going to graph this right here, it would look like this. Fg equal Fg over here. So the force of gravity as the distance increases. So this is the force, this is the distance, and it's going to have a really rapid decrease, and that's because of the squared. If you took this and you did the law of ones, which you'll see later on, 1, 1, 1 over, let's say 2. 1, 1, 1 over 1 would have been just 1, but 1, 1, 1 over 2, 2 squared is actually 1/4. So you're going down really rapidly at the beginning, but then at some point in time you get really close to 0, and it doesn't make much of a difference at that point in time. And that's why you have this little, at the end it's almost like a flat line, even though it's not. It's still going to go down. It just doesn't make a big difference. Distance is really important when it comes down to force of gravity. It's going to make the biggest difference. If you wanted to increase the gravity of something the most, you're going to get the objects closer to each other. That's the #1 thing you can do. They are directly, force of gravity and mass is directly related. One way to think about this is if I go ahead and go 1, 1, 1, 1 squared, well, the force of gravity, actually I'm not going to do this. If I go ahead and plug in 1s for everything, I know this number is going to be 1. And then if I go ahead and plug in a 2 for mass, all of a sudden 1, 1, 1 times 2 over 1 squared is going to be 2. So I know that they're directly related. If one goes up, the other one goes up. It's just an easy way to figure that out is just plug in a number for one of them, make it bigger, and see what happens to the force of gravity, whatever you're analyzing. If you're analyzing something else, if they say how does the distance change, you're actually going to have to rearrange this formula so d is equal to something, and then at that point in time you would do the law of ones. So we'll go into law of ones a little bit later as we go through some practice problems. Okay, so distance, and this is where I have a big, huge force of gravity arrow over here, because if I go ahead and go from 1, 1, 1, 1, So that would be 1, and I go ahead and change this to 2. Once again, that goes to 1/4. It goes down a lot quicker. Force of gravity goes down a lot quicker as this goes down just by one number. Inverse squared, so watch out for that. Okay, and then we went into the centripetal force unit, and the unit is newtons because it's a force. And just remember, Newton's first law says an object's going to want to keep on going straight. It's going to keep on going, maintaining its velocity if it's already moving. It's not going to want to go in a circle. So you need an outside force. And you see this guy right here struggling. He's producing this outside force to create rotation. So he has a force inwards, and that force is called centripetal force. That's the force making it able for you to have circular motion in the first place. But that force can come from other things. So centripetal force is a force, but you need something else, once again, as a label that's providing that centripetal force. And that could be the force of gravity. If you have two planets rotating around each other, this pen's messed up. Fg, if you have the force of gravity, think about this. So how am I going to get this planet to rotate around this planet when it wants to go straight? Well, I'm going to have to apply a force inwards, and that's the force of gravity between these two objects. So the centripetal force in this case would be the force of gravity. The force of gravity allowing for the circular motion. But it could be, if you have a car driving around a corner, in order to turn the corner, you need friction between those wheels. So the centripetal force could be the frictional force between the wheels. So just watch out for a equation. If they have Fc equals mv squared, so they have a lot of these variables over r. Like if you hear them talking about mass, and you hear them talking about radius, and you hear them talking about velocity, and then they say how much friction would need to be between the car's wheels, most likely, or gravity between these two objects, or in this case, there could be tension in a rope. So let's go ahead, and this pen's not working. This right here, this guy's pulling a rope, pulling it in as it's traveling in a circle. Well, that's going to be providing. So this force tension, force of friction, these all can go into that centripetal force. So just kind of watch out for any problem you might have. Centripetal force is required to pull an object inward to create circular motion. There's my little animation again. It's called centripetal force. I kind of said that already. Just restated it again in my PowerPoint. Directed inwards, this is very important. So the force is directed inwards. But if they say what would happen to the object if it was released, well, it's going to go directly straight ahead, tangent to the circle. So no matter if this guy was pulling around, round, and it was released, it would go tangent just like that. And that was what I said earlier. There's friction. This car couldn't do this little turn right here, and that car just lost it. But it couldn't do the turn without that centripetal force. This is an example of some dad being crazy and not having centripetal force when he's trying to turn that corner. Here's gravity applying that centripetal force. And planets actually, they don't go directly circular around an orbit. They follow an elliptical pattern. There's some in a future physics class, or maybe in your class, you might be learning about this Kepler's laws. And then tension. Okay, so Newton's second law applied to, so centripetal force equals mass times acceleration. Subscripts here stand for centripetal force, and force is going to be newtons, mass is going to be kilograms, acceleration is going to be meters per second squared. Once again, watch out for subscripts, or sorry, for subscripts, yeah, but watch out for the units in the equation. That's going to help you pick out which equation to use. Make sure you're looking at your equation sheet when you're picking out those equations after you make a givens list. Make a givens list every single time. You might think you don't need to, but you're going to be more consistent if you do. Make a givens list, then pick out your equations. And then if it's law 1, pick out the one that's most related to what you have in your givens list. Okay, acceleration is a vector, direction matters. So even if you change your direction but not your speed, remember scalars, vectors. Scalars are magnitude only, like 5 meters per second. Vectors are magnitude and direction, like 5 meters per second east. So if I change this direction but I don't change my speed, my magnitude of it, it is still considered velocity. It's still considered acceleration, a change of velocity. And that's because because any one of these two factors, either the speed or the direction that go into the magnitude and the direction of the velocity, only one of these has to change for it to be considered acceleration. That's why there's a centripetal acceleration equation in this section. There's your centripetal equation. Can't speak. Centripetal acceleration equation. V squared over r. It's on your equation sheet. So once again, if you have a givens list and you have v squared, you have r or a distance of some sort. It's probably going to be an r. And then they talk about what is the acceleration. You're going to be going to this equation. There's your variables. I already went over this earlier. The FC equals MAC, I haven't used that too many times. You might have to use that, but most of the time you're using the combination. So AC is actually V squared over R, and if you plug it in the place of AC up there, you end up getting your standard centripetal force equation as you see right here. Okay, and then I kind of repeating myself. This was a PowerPoint I made last year, so I didn't remember, or 3 years ago actually. So I didn't remember everything I stated in it. But circular motion velocity is often labeled tangential, and once again, that's the direction object would want to go if it was released, but it's not going to. And so the velocity in the circle whenever there's circular motion is not just called velocity, but it's called tangential. And what that does, it allows you to say, okay, direction is always going to be tangent. So even direction is changing, now you can still say velocity. But one other way to say it is just speed. If you go speed, the speed of an object, then you don't have to worry about it. Then you're just talking about that's a scalar, so you'll just be talking about that straight line right there. But in the equations you'll have, it'll probably be velocity, but it'll be talking about tangential velocity. Just watch out, if it's circular motion, they're giving you a radius, they're giving you a period, you're probably going to have to go to this. Okay, and so this is just nothing more than a specialized distance is that going around a circle. Period is the time to go around a circle. So this is all a specialized version of the V equals d over t you're so familiar with from before, in the case of circles. Okay, last equation you have to kind of watch out for is this one. We don't use it that much in this unit. We're going to use it a lot and when we get to the waves unit. So watch out for it. Frequency, look for hertz, or maybe you might be given period and time. Once again, it's going to be time for one revolution to go around once. If you see that, then it's going to be period. It's not just going to be little t time. And then you can either rearrange to period, or you can go ahead and take frequency and hertz and rearrange it to well, either way. So you can rearrange for period right here. You can rearrange it for frequency right here, depending on what you're given and what you're asked. But if you're ever given frequency and period, there's no reason why you should miss that problem. It's simple, just like you see right here. You just take the inverse of the other. Okay, good job so far. Let's go ahead and take a look at some of the math. You're riding a car and the driver slams on the brakes. Okay, so in this unit, I'm going to go ahead. I already worked out the problems a different day. So I'm just going to I want you to work these problems when there's a problem, and don't go to the next slide until you try it yourself. You should be looking at an equation sheet, and if you're not looking at an equation sheet and you're just looking at this video, pause it when I have the question before I go into the work. Most of my problems will have the question, and then later on they're going to have the work. So you're riding a car and driver slams on the brake. Your body continues to move forward until the seatbelt stops you. What causes your body to move forward? And the answer should be inertia. So once again, should have paused it there, but I kind of didn't warn you. Do that throughout this. Make sure you take your calculator out. Use your calculator. Make the mistakes before you make them on the test if you have a test coming up. Will you get her again? Mom, please. Sorry about that. Okay, a body at rest will stay at rest. A body in motion stays in motion unless acted upon by an outside force. What are the two masses and one distance that determine your weights? So if you're doing the weight equation, well, your weight comes from this equation right here. Really, truly, this would be your mass, the Earth's mass, and the distance, the radius, in this case, would be the radius between you and the center of the Earth, which is the distance between you and the center. Once again, you're insignificant. This is not the size of you. You're not a massive size skyscraper. You're a tiny little ant, not even smaller than an ant compared to this size of the Earth. The Earth was that size, you'd be tiny, tiny. I mean, America is tiny. Okay, the radius of the Earth. Okay, so let's just keep on going through these problems. Law 1s, and this is going to go ahead and go into Law 1s. If you have trouble with Law 1s, I have a Stickman Physics site. where I go into the law ones a little bit more, but I'll mention it in a second. If you don't know how to do it, just look at go forward, look at what I just did, listen to what I have to say, and then come back and try the next couple of these. Here you have what would be the difference in your weight. So if I'm looking at this, I'm thinking, okay, it's weight, FW. Right now, if you're taking this test that we're about to go into, most likely it's not going to be weight. Most likely it's going to be FG. So just watch out. You're in this unit right now. You're not in the last unit. And you're 5 times farther from the center of the Earth. So your distance is 5 times. And they don't say anything else. You just know that it's you. It's the Earth. You might not remember what the Earth mass is. You might not remember what your mass is. But you don't need to. That's the good thing about this. There's this thing called law ones where you set up a ratio. Okay, and then so you determine what you're working with. You analyze it a little bit more. You figure out what equation you're going to use. Well, FW equals mg, it doesn't have a distance in it, so that's not going to be your equation. But this m1 m2 over d squared does. And so we're going to go ahead and once again on your equation sheet it's going to say fg, but really it ends up being your weight. It's this equation right here. And you're going to go ahead and work with that one. So we're going to go ahead and use the FG equation, and we're going to figure out if this distance changes and becomes 5 times farther, what's going to happen to this number as a result. And I don't know anything about M1 or M2, but I know that G is going to be exactly the same number. It would have been 6.67 times 10 to the negative 11th, except for in this rule of ones, whatever you want to call it, but it's setting up a ratio to figure out how things are going to change later on. And so I'm just going to jump to the answer. When you set up a ratio like this, you figure out what equation you're going to use. Once you figure out what equation you're going to use, and once again, you don't need everything. You just need an equation that's related to something that's going on in the problem. And at that point in time, you pick an equation that has what you need, and you're going to keep everything the same on the bottom, and one way to keep something the same is times 1 by it. So that's why it's called rule, law ones, whatever ones, but it's setting up a ratio. And this bottom part, if you can look at the equation like FG equals G M1 M2 over D squared, and you in your head can say 1, 1, 1, so 1 times 1 over 1 squared, and that equals 1, you don't really have to worry about this bottom part, but it's a ratio, so it has to be something new versus something old. And if that old happened to be some of these problems later on, like kinetic energy, K equals 1/2 mv squared, well, this would have been 1/2. And so if you had 1 over 1/2, in that case, the ratio would have been 2 and not 1, because that would have given you a wrong answer. But in this case, in most of your equations from this unit, you plugged in 1s for everything, it ends up being 1. And so you probably can just ignore this bottom part and just do this top part, especially if you've done it before in class and it's the same thing, you know it's going to end up being 1. So to figure out the ratio, all we're going to do is we're going to plug in 1s for everything that stays the same. Once again, and when you're doing the law of ones, we're not using actual values, we're using times. And G is exactly what it was before, or 1 times. The mass of U is exactly what you were before, or 1 times. The mass of the Earth is exactly what it was before, or 1 times. But now we want to look at what's going to happen if you're 5 times farther. So therefore, the distance between you and the Earth, you're going to be out in orbit somewhere, is 5 times farther. Don't forget the square. That's mathematical in this equation. That has to stay there. And when you do this math, you end up getting 1 over 25 or 0.04. And then in just a way to kind of if you have a multiple choice test question or something like that, you can just watch out. If you went ahead and typed it into your calculator and you got 0.04 and you don't know if that is 1 over 25th, all you have to do is type 1 over 25 into your calculator and compare it. It should come out with 0.04. Just a little way of kind of getting around if you are having a little trouble with math, but it's very important to get that down. If you go into college, that's going to be the minimal. I mean, it gets a lot more and a lot more detailed. And the more you do on your own, the more you know now, the more you can sense the math, the better it's going to be in the long run. Okay, if it's 10 times farther, once again, you should try this on your own. But if it's 10 times farther, you do the same thing with a 10 in its place, and you get 1 over 100 or 0.01 times. Keep on pausing as we go through these. What is the G of 6.7 times 10 to the negative 11 tell you about gravitation? It's really, 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 really small force. That's the number. That's the number I was trying to come up with earlier, but I ran out of space. That's tiny. So you need really, really massive masses for it to be effective. And around where you're at right now, watching this video, that's the Earth. I mean, you don't sense. You're attracted to your pencil. You're attracted to your neighbor. You're attracted to your computer, but you don't feel it because it's very weak. It's not gonna sense a mass of 20, 30, 40, 50 kilograms. It's gonna take hundreds of thousands of kilograms to even sense it whatsoever, and a pretty decent or really close, but nothing you could just sense the Earth. Okay, so here's the next problem. Let's go ahead, and this is where you need to be typing these numbers, and if you're not typing these numbers, then you're gonna make the mistakes when you don't want to make them. Make them now, try them out, come back to the video if you're still making the mistakes tomorrow after you realized how not to make the mistakes. So here we have our mass. On your equation or on your paper, you should be writing M1, M2. You should be writing, okay, oh, that's your D. Okay, what is it asking you for? Their traction. Well, if you don't know, okay, it doesn't say force of gravity. So how do I know this is force of gravity? Well, it's talking about masses. It's talking about distances. Fg equals capital G M1 M2 over D squared. That's going to be the force of gravity. Force of gravity is always going to be an attraction. That's going to be important. As we go into next year, we're going to talk about electrostatic force, which can be a repulsion too. Force of gravity is always going to be attraction. You're attracted to anything that has a mass. You're attracted to a cookie. You're attracted to a paper towel, a little bunch of things I have around here. Okay, and then so you have your givens list. Once you make your givens list, this is what you should see. Then this is not a law of ones problem. So G has to be 6.67 times 10 to the negative 11th. Once again, the tip is if you know your exponent button in your calculator, you can type in 6.67 and then the exponent button, you should see an E that looks like that, most calculators. If you see an E that looks like, I'm going to write up here because I don't want you to see it down here. See the E looks like this, you're probably doing it wrong. Also, make sure that you don't want to see an E with like, you're not taking this, you're not going to go ahead and, you should not see it to the exponent. Some calculators do that. It should be right next to it. Once you type an E, this is seen by your calculator as times 10 to the power, and the next thing it says, it throws it to that power. That's all you have to see. If you don't know what I'm talking about, do the math, see if you get the answer, and then compare it. And if you got the right answer, then you're doing everything just fine. But if you don't, come back here and maybe see if you can understand what I'm talking about. Okay, so this is what you would do when you're typing this in. The biggest area where I see mistakes, this squared right here. Double check. If you're not getting this answer, you didn't get this answer, did you square this number? Another mistake is some people will just leave out this times 10 to the negative 11. Sometimes a lot of people will just leave out this G altogether. So make sure you put that G in. I've seen too many problems that have the kids going 70 times 85 over 2.5 squared, and they're not getting the right answer. Don't forget to have that. It's another thing I see. So as I go through this, I'm just telling you what to watch out for. If you're making a mistake, it's probably going to be one of these things that I'm talking about. Did you forget the squared? Did you forget the G, the actual real G that should have been in there? And there's your answer. I rounded a little bit. You probably had a little different number. And if you had, well, this one, it would have been 0.123456763. That's what it would have looked like. Just a reminder, to the negative 8th means you're taking this number right here and you're making it smaller by 8 spots. So if you see, I always look at the exponent or the scientific notation, and I go from there. If it's a negative, I'm making this number smaller. If it's a positive, I'm making this number bigger. And once again, this is the nice thing about scientific notation is by zeros, so you can just move the decimal over to figure it out. And then don't forget your unit, the Newton. Okay, next one, you're solving for mass. I'm going to go ahead and I rearrange this in the next slide. I'm going to rearrange it just for you so you can see what's going on. That's why you get a little extra practice. Do it on your own and then double check. Anytime you're solving for mass, just get to practice. Go ahead and rearrange it every single time. So Fg equals G M1 M2 over D squared. And if I'm trying to solve this for mass, what you have to realize, mass is up top, so it can stay up top. Just to think about math. If I say 1 dozen equals 12, or I say 12 equals 1 dozen. Both of those are true statements. Both those work. But this is what I'm talking about. If it's in the denominator, if let's say I'm trying to solve for this and I get rid of all this other stuff, the G, the M1, the M2, I'm actually left with 1 over, in that case it would be D squared. Well, you can't do that. You gotta. That's like saying 1 dozen equals 1 over 12, and that's an incorrect statement. So what you have to watch out for is not whether it's on the left or right, but whether it's in the numerator or the denominator, because if you get rid of everything else, you're going to be left with this 1/12 equals a dozen, which is not correct. If you're good at doing the inverse, don't even listen to me. If you're good at doing the inverse, you can get your final answer that way and you can take the inverse of it, but that's not going to be the best approach. So what we're going to do here, we want to get rid of, we don't have, actually, we want mass up top. This is good. We go ahead and we want to get rid of the d squared first. We have it d squared divided, so we're going to multiply both sides by it. So I just read it. And that's going to get the d squared over here. And then next, what we're going to do at that point in time, we just want to get rid of the g. We can nicely get rid of the g and the m squared by dividing both sides by g and m, or not m squared, it's m to the second mass. And at that point in time, it's already done. M1 equals, and I just wrote it different. I'm going to rewrite it with m on the left side. But at this point in time, you can just flip the sides, keep everything exactly where they're at. Fg and d squared up top, capital G and M2 down the bottom, and just a word for the wise, double. Even if you could have 1,000 parentheses, it's not going to hurt, but at least have an extra parentheses around the bottom numbers, because your calculator will not keep these numbers together. This is very, very important for you to be successful on these kind of problems. Too many students make mistakes on when you get to the denominator on the bottom. Okay, so I'll erase my work because it shows it next. Okay, there we go. And so that's just a slide that shows all of that being done all at once. And then double check, your answer should have been 55 kilograms at the end. And if you did not get the answer, what happened is, and I was missing, if you typed this in exactly like I had it a second ago, you would have got the wrong answer, because your calculator would have took this number times that number divided by this number and not divided by this as well. It would have taken all this stuff, put it in its memory, and then it would have multiplied the number by 65. So you would have a far different answers. Just watch out. If you're not getting the right answer, make sure you come back here and have that extra parentheses around the bottom. Once again, what you saw before, if you typed it just like that into the calculator, you would have gotten there. You would have got a mistake. It would have not been the right answer. It would not have been 55. But having this extra parentheses around the bottom, you're going to get 55 or something rounded to it. Once again, I did this problem last year, or 3 years ago actually. So let's keep on going. Okay, Mercury is 5.691 times 10 to the 9th meters away from the Sun. If the Sun has a mass of 1.99 times 10 to the 30 kilograms, and Mercury has a mass of 3.30 times 10 to the 23 kilograms, what's the force of gravity between these bodies? At this point in time, once again, you should have paused it. You should have made a givens list. If you didn't, do that. And after you do that, you take a look and you pick your right equation. And right now, it's in order, so you're seeing more of the force of gravity equations. A lot more when you have, if you're using the E button, exponent button that I told you about earlier, you're less likely to make a mistake, but this is another one. Once you start getting into scientific notation, if you're not including an extra parentheses, depending on how you type it into your calculator, you could be getting an error. You might not be getting this. So if you're not getting this one right, double check two things. Make sure you have extra parentheses around the bottom, and also make sure that you are squaring your d squared is actually d squared. Okay, you have a 2,000 kilogram truck traveling a circle with a radius of 90 meters, 15 meters per second. Right now, I'm sensing that centripetal force equation because it has mass in it. And that's what you should do, but this actually, I didn't read it all the way through. That'd be fine. Make a givens list. You should have made a givens list. And if you didn't make a givens list, and once again, if you're just watching this video and not doing anything, you're not going to get much out of it. Make sure you're doing the problems before you see what I did. Well, I was thinking centripetal force, but I didn't actually read what it was asking for. It's asking you for the centripetal acceleration, and I have everything I need, and then you have an equation sheet that has this nice little beauty right here. AC equals v squared over r, and you have everything to plug in right there. It's nice and neat. Throw it in. Don't forget the squared. The biggest students, the students that miss this the most, they're going to be the ones that just don't know where to find it. They haven't used the centripetal acceleration equation enough. So this practice that you're doing right now is a good thing. Okay, student spinning a stopper. Most of you did this lab in school. Around its head with a centripetal force of 5 newtons and a radius of 0.3. It takes 0.4 seconds to make 1 revolution. This is key right here. For 1 revolution, you see that 1 revolution, you're like, hey, it's period. If you see something else, it's just time. But if it's to happen, one thing happening, in this case, it's a circular motion, so it's going to be a circle, of one complete circle, the time it takes for one complete circle, that's period every single time. So you make a givens list, and after you make a givens list, so here's my little givens list right here. I'm asked for the velocity, so I look in the circular motion section. I'm not going to look at the v equals d over t because I'm in circular motion right now. You're in circular motion right now. Make sure you look at this section, the equations from this one, and you'll see v equals 2 pi r. Over t. If you can't find your pi button, just to type in 3.14. That's what I usually do. And then your number might be slightly rounded different. After you do that, then you're trying to solve for the massive stopper. Once again, a little bit of algebra. Mass is on top. So what I can do is I can go ahead and multiply out the radius. When I multiply out the radius, now I have velocity here that I don't want and velocity squared I don't want. Divide out the velocity squared. Once I divide out the velocity squared, I'm left off with mass, this one right here. Mass equals Fc times r over v squared. And you should get 0.068. Once again, the rounding might be a little bit different on what you're doing. But you'll see, if it's a free response section, you most likely you show the work, you're going to get the grade. Your teacher's going to realize there's not going to be that far off. It's going to be close enough where the teacher's going to look at the work. Work's not there though, you might not get credit. So make sure you're showing all the work that you're doing. What's the force of gravity between two objects? So sorry, the force of gravity between two objects is 400 newtons. The mass of one object is triple. Oh, you hear this word like tripled or doubled or halved or quartered or whatever, you already should be thinking about the law once. What is the new force of attraction between them? Okay, I also see attraction. So I'm going to go to the force of gravity equation almost every single time. And that's what happens here. So if you go to the force of gravity, you do the law ones, everything the same down the bottom, or one, and only one of the masses tripled, and your answer is going to be 3 times. But this is an extension to the law ones. They actually gave me a force in the first place. So if they ever give you a force of gravity like this, you're actually not going to use it in the law ones until you're done. The force of gravity was this, but then you see tripled. This is the key. Tripled, doubled, whatever. You see these kind of words, you're probably going to do law ones and you're going to come back and use this later on. What's the new force? Well, it's 3 times. Well, 3 times, what does that really mean? Well, that means 3 times what it was before, and 3 times 400 is 1200. Throw the newtons on the end and you got the right answer. Okay, I don't know if I skipped something, but this says 12. How does the gravitational force between two equal masses change if the distance between them is increased by a factor of 3? Law once again. 111 over 3 squared over 111 over 1, once again squared, but you don't need to do that once you realize it's going to be 1 anyways. And then you'll get 1/9. And if you have a fraction on your multiple choice section or whatever of your test, you don't know 1/9 is whatever number, just type it in and you'll see the fraction. Or if you see a fraction on your paper that you just finished off the free response section, you have to match it up with something else. Type in the other numbers. Type the numbers in the multiple choice section over and over and over until you get to the decimal place that you have on your paper you just wrote down. Okay, draw the path the ball would take if a string broke at 1, 2, and 3. Okay, so this is where the tangential velocity, if there was no centripetal force, well, it would just follow a straight line tangent to the circle. If it spun out here, if you lost the centripetal force, if a string broke, you'd go directly, either one of these spots, it's going to go straight ahead. And tangent, if you don't know what tangent is, it's just a line along an arc. So anywhere, these are all tangent. I'm drawing tangent lines. Actually, that wasn't tangent. These are all tangent. These are all tangent. Go back to the answer. It's going to look something like that. How would you describe this motion? Circular motion. To describe the acceleration ball, its accelerates and its direction always changes inwards. So since it's changing direction, it's acceleration and not just constant velocity. But you can say tangential velocity to get away with it for the math. Describe the velocity of the ball. The direction constantly changes even if the speed or magnitude is constant. Okay, force is acting in which direction? This is centripetal force, always directed straight in. If a car is driving around a circle, what keeps the car moving forward? Well, inertia is going to keep it going forward. But if you have friction between your wheels, you're going to have, that's going to be the centripetal force that's provided that's allowing you to go in the circular motion. Once again, centripetal force is usually another force that just happens to be the centripetal force. So you need centripetal force, but often it's the force of gravity, force of tension, force of something else. If you did the lab, it's with the spinning bobber, the rubber stopper. It was the tension in the rope, which was produced from the rubber stopper wanting to go straight ahead while it wasn't allowed to because that weight that was hanging down. If you didn't do the lab, don't worry about it. But that's what was happening. The weight was the centripetal force, and it was seen in the tension that was pulling. It was on that string that was pulling. Once again, if I'm going to draw it in here, right here, it was pulling inwards, and the weight just happened to be hanging down. But all that really mattered for centripetal force is there was something pulling it in, allowing it to turn constantly and make a circle. If the velocity of the car is 1/3 of what it was, how much different is the centripetal force acting on the car if all other factors remain constant? Law of ones. So in this case, the velocity of the car is 1/3. They're talking about velocities, so that's what tells you you're not going to the force of gravity equation. This is just some of my old work right here. The velocity is in the centripetal force equation. So you're looking at the right equation, and I should have done this over 1, but 1 squared over 1 would have been 1. So I just really can do the top and get away with it, and ended up being 1/9. Satellite orbit at the same velocity with 2 times the amount of gravity. What would happen to the radius of the orbit? Well, it's going to go ahead and same velocity, 2 times, we're talking about velocity here, 2 times the amount of gravity. And this case, though, if you find the equation that's most related, in this case, it's going to be the centripetal force, and you have to rearrange it for what you are analyzing. In this case, you're analyzing the radius of the orbit. So to rearrange this is like what I said, the 1/12 doesn't work. It doesn't equal a dozen. This is on the bottom. You need to go ahead and start by multiplying it out. Now you have it on top. It can stay there. You want it there. You want to divide out the FC. You divide out the FC. When you do that, you get this equation right here. Then you do the law of ones with it. 1, 1, 1, and the thing that doubled was the force. In this case, force gravity. Once again, force gravity can be the centripetal force, which it is in this case. And then you get 1/2. It's 1/2 times whatever it would have been. If you knew a number, it would have been 1/2 times that number. The string breaks when the tension is just under 300 newtons. If you're swinging a 5 kilogram mass over your head in a circle with a radius of 5 meters, at approximately what speed will the string break? Okay, so a problem like this says string breaks at 300 newtons. So if our centripetal force is greater than, let me go and draw greater than 300 newtons, it's going to break. That tension in that rope is going to break, and that ball is going to go flying. Once again, that's not really tangent to the circle, if I draw it correctly. It's going around in a circle, circle, circle. That ball is going to go straight ahead tangent to the circle. So what tension does the string, I can't speak anymore, it's late at night, the string break? You're going to go ahead and say, let's go ahead and figure out what that when centripetal force is 300 newtons, that's the maximum that can happen. So you're going to do the centripetal force equation, but you're trying to solve for velocity, so you're going to have to do a little rearranging. So let's take a look at this equation. V is on top. Once again, it's V squared, so we're going to have to get rid of the squared at some point in time. V's on top, but we're going to go ahead and get rid of the R, and then we're going to get rid of the M by dividing both sides by M, and then we're going to get rid of the squared by taking the square root of both sides, and that's what it ends up being. And then you plug in your numbers, and you can go from there. And you should have 17.3 meters per second. Use the universal gravitational equation for the questions below. How are force and distance related? Sketch the graph of the situation. And there you go. They're inversely, it should be inverse squared related, because it has a bigger effect. If you only see inverse, then you can probably go with that, but inverse squared, it just tells you that it's much bigger. It's causing that curve that you see there. Force and mass, well, if you're trying to figure out that one, you get the Fg equals G m1 m2 over d squared equation, and you go ahead and say, okay, if if everything was the same, 1, 1, 1 over 1, Fg would have been 1. But if you went ahead and made mass 2, 1, 2, 1 over 1 is actually 2. So since 1 went to 2, 1 went up, or Fg went up when the mass went up. That's directly related. And once again, I did this many times in this video. 1, 1, 1 over 2, it doesn't just go up. It doesn't just go down half, it goes down to a quarter. And that's where that whole squared comes into play. Okay, Brad and Josh are on a merry-go-round. What's Brad's linear speed? What's Josh's linear speed? So once you know how to do the equation, these are pretty easy, but it just takes a practice. And you write down your variables. The period is the same. They're on a merry-go-round. One's a little closer to the center, and one is further away from the center. And so therefore the time it takes to get around is going to be the same because they're on the same merry-go-round, so the period is going to be the same, but the radius from the center is going to be different for each of these guys. And so you just do the centripetal force equation and you figure it out. And then just something to note, and I have on Stickman Physics again a video of this going on. Okay, so if you go ahead and you have this guy going around the circle in the same time as this guy went around the circle, this guy traveled a further distance. So the further out, the greater the tangential velocity. So that goes up the further out you go. It's okay. This is asking as you go closer to the center. So if you go closer to the center, we're going to opposite. You're going to go ahead, and in that case, as you go closer to the center, then v is going to go down because you're traveling less velocity in less distance in the same amount of time as this guy would have done in the same amount of time. Once again, if they're on a merry-go-round, whatever's here and whatever's here and whatever's here is going to end up at the same spot at the same time. Not the same spot, but the same, that spot when it comes back to this finish line. Treadmill spins once every 1.2 seconds. What's the frequency? So it's spinning once every, here's your key. This is period. What's the frequency? You got the F equals 1 over T equation. And it ends up being, once again, don't forget the units, hertz, 0.83 hertz.